Hey everyone, since we're at the end of Chapter 7, what we're going to do today is spend some time going through some AP questions having to do with the content we've covered in this chapter. So some will be multiple choice and some will be FRQs. We're going to go through a set here in the video and then you'll have some time to practice on your own. So let's go ahead and get started. So the first one, we're given a function, and again, this is a function defined as an integral, and we're being asked to find that derivative. So hopefully by now we recognize that this is just a fundamental theorem of calculus, right? Because if I'm trying to find f prime of x, I know that's just the derivative with respect to x of this integral. So now that I know that, I'm going to check a few things. First, I'm going to check that my lower limit is a constant, which it is. My upper limit is just x, not a function of x, so that means I'm just going to substitute it in for my dummy variable in the integral. So this answer is just going to be e to the negative x squared, which is going to give us choice E. Okay, number 2. So if capital F and lowercase f are continuous functions such that f prime of x is equal to f of x for all x, then the integral from a to b of f of x dx is. Well, let's see here. I notice that my answers here are all expressed as functions of capital F. What I have to decide is it capital F or f prime that's going to be the integral. So let's look at that integral. The integral from a to b of f of x dx. Well, we were told that f of x is just capital F prime of x. So I'm going to rewrite that integral from a to b. Instead of f of x, let's use that equivalent function, f prime of x dx. Now, I know the antiderivative of f prime of x is just going to be f of x. And I'm evaluating that lower limit of a, upper limit of b. So we know when we're evaluating an integral, we're just going to evaluate that function at the upper limit, and we're going to subtract the value of that function at the lower limit. So we get f of b minus f of a, which is going to give us choice D. All right, number 3. Looking at that equation, what I would hope you would recognize once you see this dy dx, hopefully you recognize that we have a differential equation. And this one is just in terms of x, so we don't have to worry about separating any variables. So in order to solve for y, we need to go through our steps for solving a differential equation. I'm going to rewrite my equation here. Cosine of 2x. Remember, our first step is to multiply by dx, so we get y's on one side and our x's on the other. Once we've done that, we're going to integrate both sides. Okay, so now I'm going to get y equals. Now here, I know the antiderivative of cosine 2x is going to be sine 2x, but I also know that if I were to differentiate this, I would get an extra factor of 2. So my antiderivative needs to have a factor of 1/2. Now, you could also use u substitution if you can't see why this 1/2 would be here. You're going to get the same answer either way. Now, don't forget, on one side, we need the plus c, because this is indefinite, or I don't have an initial condition to solve for c. So we have our plus c here. So at this point, this is going to be our answer, which is going to give us choice C. All right, let's keep moving along here. Number 4, let's see, I have the integral from negative 2 to 2 of x to the 7th plus k dx equals 16, and I need to solve for k. So the important thing to note here is this k is just some constant. So we're going to treat this just like a problem, any other integral. So I'm going to rewrite it here. Negative 2 to 2 of x to the 7th plus k dx. All right, so I know to find that I need to anti-differentiate this. So I'm going to get x to the 8th over 8. Now, this is just a constant. So if, let's say this was 2, we know the antiderivative would be 2x. So in this case, our antiderivative is just going to be plus kx. And we're going to evaluate this antiderivative from negative 2 to 2. So I'm going to evaluate at the upper limit. So I'm going to get 2 to the 8th over 8. Let's see, plus. Remember, our 2 is going in for x, so I'm going to get plus 2k. Then I'm going to subtract the value at the lower limit. So I'm going to have negative 2 to the 8th over 8, and then minus 2k. So as I'm looking at this, since this is an even power, negative 2 to the 8 is going to be the same as 2 to the 8th. So when I subtract those are just going to cancel out. I don't even need to worry about simplifying 2 to the 8th. So now I have my positive 2k, and then I have minus a negative 2k, which gives me another 2k. So I've got 4k, and we were told up in the problem that this is equal to 16. So now we can set that equal to 16, divide by 4, and we get a value for k of 4, choice D. All right, here's one. Number 5, this is what I've told you you are pretty much guaranteed to see on the AP exam. And this gives you a good idea of how they combine these questions. So clearly we have a differential equation. It's going to be separable because it's in terms of x and y. We're going to be working with a slope field, and they're going to be asking us to solve that differential equation. Again, pretty typical for an AP question. So the first part is asking us to sketch the slope field for this differential equation. So the first thing I try to do is look again for patterns where I can knock out a bunch of points at once. So I know first of all that this is going to be 0, definitely where x is 0. So x is going to be 0 along the y-axis. So I'm going to make all those slopes 0. Now, I also know this is going to be 0 when y is equal to 2. So that's kind of nice because I've knocked out a good chunk of points there. So then for the rest, I'm just going to plug them in. Here I have the point 1, 0. Excuse me. So 1 to the 4th gives me a positive 1. Y is 0, so I have negative 2. So I have 1 times negative 2, or negative 2. Now here at 1, 1, again I have 1. 1 minus 2 is a negative 1, so that slope's going to be a negative 1. Now up at 1, 3, I have 1. 3 minus 2 is 1, so I'm going to get a positive 1 for my slope. Now at negative 1, 0, again, negative 1 to the 4th still gives me a positive 1. 0 minus 2 is negative 2, so my slope is going to be negative 2. Negative 1, 1. Again, my negative 1 to the 4th still becomes a positive 1. 1 minus 2 is negative 1, so that slope is negative 1. Then for my last point, negative 1, 3. Negative 1 to the 4th is a positive 1. 3 minus 2 is 1, so I have a slope of 1. And there's my slope field. All right, so now for part B, it says while the slope field in part A is drawn at only 12 points, it's defined at every point in the xy plane. So describe all points in the xy plane for which the slopes are negative. So here they're not just asking for the points that you've sketched in your slope field. They want to know all points. They kind of want to know, in general, how would I know where slopes are negative? So if I'm looking just at my slope field, it kind of looks to me like slopes are negative where y is less than 2. This is kind of a boundary line where everything below it seems to be negative, which would make sense. If y is less than 2, it's going to make this factor negative. Now, the only values I have to exclude are here where x equals 0. Because if x equals 0, this derivative is going to be equal to 0, not less than 0. So I'm going to say dy dx is less than 0 when y is less than 2, and x is not equal to 0. Those are my two conditions that'll get me a slope less than 0. Y less than 2, so under this line, and I'm excluding these points where x equals 0. All right, last part for this question. Find the particular solution, y equals f of x, to the given differential equation. So they're talking about this equation here, with the initial condition f of 0 equals 0. So this means, right, particular solution means I need to solve for c. I shouldn't have a plus c in my answer. So let's go ahead and do this. I'm going to copy down the problem. dy dx equals x to the 4th times y minus 2. First thing I need to do is separate the variables. So dy over y minus 2 equals x to the 4th dx. I'm going to scoot this up a bit. Okay, now that I've got everything separated, I'm going to integrate. So on this side, I'm going to get the natural log of the absolute value of y minus 2. I don't need to worry about chain rule because there's nothing in here that would trigger the chain rule. And that's going to be x to the 5th over 5 plus c. So I'm going to go ahead and use my initial condition, see what's going on here. So f of 0 equals 0. So I've got the natural log of 0 minus 2 equals, well, x is 0, so this term drops out, and that's going to be c. So 0 minus 2 is a negative 2, but I have the absolute value, so my c is going to be natural log of 2. So back to my equation. I'm copying everything down, but I'm plugging in my c, plus the natural log of 2. Now, this is going to be very common, so I want to make sure we all understand. Whenever we have the natural log, in order to isolate y, I need to take both sides and do e to the natural log of y minus 2, and I'm going to do e to this whole expression. Okay, we're not multiplying by e, but we're raising that. So e to the natural log of the absolute value of y minus 2 equals e to the x to the 5th over 5 plus natural log of 2. Now, we know, using our exponent rules, this is e to the x to the 5th over 5 times e to the natural log of 2. Okay, I'm going to jump up here. Now, since I have e to the natural log of the absolute value of y minus 2, these are inverses, so I'm just left with absolute value of y minus 2. Now, I'm going to simplify this. E to the natural log of 2 is just 2, and then I have e to the x to the 5th over 5. Now, I can't just drop the absolute value. I have to be a little careful here. So when I drop that, I know I have either plus or minus e, or 2e to the x to the 5th over 5. I'm going to add 2. So I have plus or minus 2e to the x to the 5th over 5 plus 2. Now, we don't want a plus or minus in our answer. Here's where we're going to go back and use our initial condition to decide what this should be. So if x is 0, I'm going to get e to the 0 is 1. Now, if this were a positive, I would have 2 times 1, which is 2, plus 2 is 4. But that's not what my y value is. My y is 0. So I actually need this to be the negative 2. So the negative 2 plus 2 will give me 0. So my solution is going to be negative 2e to the x to the 5th over 5 plus 2. Again, because then if I plug in 0, I get e to the 0 is 1. 1 times a negative 2 is negative 2, plus 2 is 0, and then I match my initial condition. So that's my final answer. So we have to be really careful with those absolute values that we're not just dropping them without considering the plus or minus. Okay, what do we have left here? We've got one more to go. All right, so it gives us, let f be a function with f of 1 equals 4, right? So what they're giving us is a point there. 1, 4. So such that for all points x, y on the graph of f, the slope is given by, 3x squared plus 1 over 2y. So since that's a slope, right, what we know really is dy dx, our slope, is 3x squared plus 1 over 2y. All right, so let's see what we need to do here. The first question says find the slope of the graph of f at the point where x equals 1. Okay, so I know I want to find the slope. Well, that's just our dy dx here. So where x equals 1, so that's fine. I know what to plug in for x. Now, where x equals 1, they told us f of 1 equals 4. So we know our y value is 4. So we're using this point 1, 4 to figure out the slope. So all I'm going to do is calculate dy dx at the point 1, 4. So that gives us 3 times 1 squared plus 1 over 2 times 4. So 4 over 8, or 1/2 is our slope at that point. Okay, now in part B, they're asking us to write an equation for the line tangent to the graph of f at x equals 1, and then we're going to use that to approximate f of 1.2. So again, for a tangent line, I need two things. I need a point, and I need a slope. Well, the point they had given us, if I want it at x equals 1, I know the point there is 1, 4. And the slope of that point we just calculated. It's 1/2. So our equation is going to be y minus 4 equals 1/2 times x minus 1. So now I'm going to rewrite this. Back when we did our linearizations, right, we used the tangent line to approximate a function value. We changed our y to L of x, and we just moved everything else over. So now, if I want to approximate it, I want to approximate f of 1.2. I know that's approximately my linearization at 1.2, because remember, this is the tangent line, so it's just approximating values very close to x equals 1. So it's not the exact value, but for values close to 1, it should be close. So I have 4 plus 1/2 times 1.2 minus 1. So 4 plus 1/2 times, we have 0.2. Well, 1/2 times 0.2 is 0.1, so that value is approximately 4.1. So f of 1.2 is approximately 4.1. Okay, I'm going to box that here. Now for part C, here we go. They want us to actually find the function by solving that separable differential equation, and we have initial condition f of 1 equals 4. So let's get that equation down. So first thing we do is we separate our variables. So I have 2y dy equals 3x squared plus 1 dx. I'm going to integrate both sides, and luckily these are going to be nice and easy to work with. So integral of 2y is y squared. Here I'm going to have x cubed plus x plus c. And now I'm going to use our initial condition. So we have f of 1 is equal to 4. We're going to use that to solve for c. So I have 4 squared equals 1 cubed plus 1 plus c. So 16 equals 2 plus c, or c equals 14. So now I go back, and I'm going to plug c in, x cubed plus x plus 14. So y now is plus or minus the square root of x cubed plus x plus 14. So again, we go back to our initial condition to decide if I want the positive or negative. So we know our x value in our initial condition was 1. So if I plug that in, I'm going to get 1 plus 14. That's going to give me 16. Now, I want my y value to be a positive 4. So square root of 16 is a positive 4, which means we get rid of our negative, and we're just going to take the positive square root. So x cubed plus x plus 14. Square root of that. Okay, so that is our solution. Last piece here, it wants us to find f of 1.2. Now, this is the actual curve. So to find f of 1.2, we're just plugging in here. And this gives us the actual function value. So I have 1.2 cubed plus 1.2 plus 14. Here, we will use our calculator to do this. To find mine. All right, here we go. All right, so I have the square root, of 1.2 cubed plus 1.2 plus 14. So I get 4.114. And so we can see our linearization was a pretty good approximation, again, because 1.2 is very close to 1. So there's some practice with the AP, and again, you'll get plenty of chance in class tomorrow to go through lots of problems on your own. That's it.